I invited Azriel and Keith to give a talk on counting neutrinos at the South Pole. I was actually at PyCon in, was it May? Yeah, I was at May, and Keith gave this talk there at PyCon. And I think neutrino detection and just physics in general is pretty cool. And but he was at PyCon giving a talk, and what's interesting is like not only is it like got the whole physics aspect where you're detecting neutrinos, but also there's this whole software aspect. A lot of the control code is written in Python as well. I guess that's why you got invited for PyCon. And so it's a pretty cool talk. Lots of good pictures and things like that. So I'll leave it off to you guys to start up. Thanks for coming.
Hi. So I'm Azriel, and I'm the physicist in our two-tag team. So I'm in charge of the nerdity part of the talk. Do we have a little thing? Or oh, we'll just switch here. It's good. So before I start, let me just talk about this first picture. It's an aerial of the South Pole, actually, right, at 90 degrees south. And what you see in the middle is what's called a drill camp, the big machinery used to make deep holes, which Keith will talk about in the ice for our detector. It's mostly flat and high over there, and he'll describe more. So we went all the way there to build a neutrino detector, which is called IceCube. And the first few minutes I'll spend trying to explain the motivation for us going that far to detect an elementary particle. So one of the main questions that IceCube tries to address is what is the origin of the cosmic rays? So cosmic rays are actually ubiquitous. They're all the time hitting the Earth from all directions. But their origin, where they're actually produced, is still an open question. There are lots of theories, but no final clues yet. So they were discovered in 1912 as essentially the detectors on the ground and then flown in the atmosphere. What we do know is what they're made out of, at least when they're hitting the Earth. It's a whole bunch of mostly protons and smaller nuclei, gamma rays, essentially photons, and electrons. What's striking about these cosmic rays is that they span a very large energy range. There is all the way from MeV, mega electron volt energies, which is small energies for particles, all the way to these 10 to the 20 electron volts. That energy, 10 to the 20 electron volts, is equivalent to a tennis ball going fast. And what's striking is that amount of energy is coming in a single particle. So the big question is there, what they're out in outer space that can accelerate a proton to that amount of energy. So for these cosmic rays, we know that some of them have to be produced in the sun. There's also a pretty good hypothesis that in supernova explosions, when the star collapses, there is shock waves that can accelerate particles to very high energies as well. This thing says I've been speaking for 25 minutes. I'm sorry. Sorry about that. But as I said, the origin of these, especially the highest energy cosmic rays, is still unknown. And it's a mystery that hopefully the neutrino observation of the sky can help answer. And I'll say a word as to how that happens. But before, let me describe a little bit of what the neutrino itself is. So the neutrino is an elementary particle, much like the electron or quarks, that was originally inferred, not discovered experimentally. There was a process called beta decay, in which a proton and an electron come out, and there was some missing energy. Some experimenters could not see the balance of the energy. So this gentleman over here, Wolfgang Pauli, in 1930 hypothesized that there was a particle that was carrying away the energy that was not observed in the experiment. So these neutrinos have no charge. unlike the electron. So they are neutral. They have very tiny mass, and they're going, essentially, they go through kilometers or actually light years of material without interacting for the most part. Just to give you an example, billions of them are actually going through every person, every centimeter square all the time. And to give you an idea of how often they actually do interact, the first professor I had in astrophysics gave this number that about 1 neutrino per 70 years interact in our body. So there's a whole bunch of them. Most of them just go through, and one of them in 70 years will interact. And he claimed that's the cause of death. So there are lots of them. They rarely interact. So what's the challenge for the experimenter is making detectors that are big enough and sensitive enough that can see one of these particles. So big enough because the fluxes are big, but the interaction probabilities are very small. So typically what's done, and Keith will show more, and I'll say some, is you use a very large body of transparent material, water or ice. Ice is the case of, in the case of ice cube, for their detection. Now, why try even to look at the sky and look for neutrinos? Well, we have already observed cosmic rays, and this slide tries to explain that. Imagine, do we have a pointer? Actually, I'm still kind of no. It's okay. This is not a pointer, right? No. So imagine the object on the far up left being a very distant galaxy with some process inside that can accelerate particles. What typically is accelerating inside these bodies is charged particles, because they're easy to accelerate with electric fields and magnetic fields. You can push a particle around. So typically what you get is protons going from these objects. The protons, however, when they travel from a far distance galaxy to ours, they undergo magnetic deflection. So when they get to Earth, they don't point back to where they actually originated. So they essentially get isotropized, and you cannot tell what object in the sky made it. On the other hand, protons, if they interact, they can produce photons. We call them gamma rays when they're at high energy, or neutrinos. Photons are good, and that's how we actually look at most of the sky. We look at photons of low and high energy to get images, and that's where we get most of the information we know about the universe nowadays. The disadvantage of photons is when you're looking at very high energy, such as in these objects, the photons don't travel cosmological distances, so you can learn about the vicinity of the universe and not far away. Unlike neutrinos come out of the source and they travel essentially in a straight line, and basically nothing stops them, not even the detector, unfortunately. That's why you need these large detectors, and with a little bit of luck, you catch a few. So essentially what we're trying to learn is how these objects work, and if we learn about where the neutrinos come from, that will point us to where these cosmic rays of very high energies come from, because they are produced essentially in the same location. By the way, you're most invited and welcome to interrupt when something is not clear, or just have an itching question. So here I have a few pictures, all from essentially photons that have been made of the objects in the universe. It's kind of a collage, and you cannot see it very well. Maybe you see it better on that monitor. Objects that are extragalactic. Sometimes it could be like a big galaxy with a huge, massive hole in the middle, black hole, in the middle, that accelerates particles, or objects that are more nearby in our galaxy, in which either you have a large magnetic field or a fast rotating star that can produce acceleration of protons, and thus a production of neutrinos. So this is a collage to give you an idea of the kind of objects that, when we look at the sky, in the neutrino sky, we're hoping to see neutrinos from these sources, of which we know something by having looked at the photons that these sources emit. And just to give you a more specific example, is here's an active galactic nuclei, which, as I said, is the center of a galaxy. There's a supermassive black hole that's all the way at the top left of the picture, and then it produces jets where material gets accelerated and where protons are presumed to achieve these very large energies that are cosmic rays are measured to get at. So they're very bright. They can be very, very far away, and are those are some of the best candidates for being producers of neutrinos that we're after. So this is kind of the cosmic ray side of the thing, which is a question that's a long-standing astrophysics question. There is another wrinkle of what this neutrino detector can do, which is related to dark matter. Some of you may have heard about dark matter. Dark matter is essentially thought to be 23% of the mass of the universe in a particle that we don't know what it is. So we're pretty ignorant about its actual nature of the particle, but we know it's there because of its gravitational force. So another thing that a neutrino detector can do, and we're pursuing, is trying to detect these dark matter particles. In some models, these dark matter particles would accumulate in big objects such as the sun, and then they would find a dark matter particle with another dark matter particle will annihilate and produce as a byproduct neutrinos. So what we're doing is looking to see in the direction of the sun where there are neutrinos coming from the center of the sun, and if so, of very high energy, and if so, maybe a hint that actually there is dark matter being accumulated in there, and it will give us hints about the nature of the dark matter particle. So going back to what you need to detect these neutrino particles. So what you need is as I said, because they interact very weakly, you need a very large volume of a transparent medium. Transparent, why? Because the neutrino comes in and it's neutral, does nothing, but when it hits a nucleus of the material, it will produce a charged particle as a result. And when the charged particle travels fast through a transparent medium, it will make a little bit of light. And it's that little bit of light that we're trying to detect. It's called Cherenkov light. And that's why what you are after is a large transparent medium. The other thing that you need for a neutrino detector to work is good shielding against charged cosmic rays. Neutrinos events are always going to be very few, for the reasons that I mentioned before. So you need to hide essentially from all the charged particles that are hitting the Earth all the time. So typically that forces you to be 1, 2, 3 miles underground. Actually, the more the better, to stay away from events that are not what you're interested in. So the typical examples of what's used is water, deep water preferably, and in the case of deep water, you can just go to the ocean to run an experiment. A deep lake such as the Baikal lake in the ex-Soviet Union, or ice, which is what IceCube, our experiment, uses. So this is a slide that kind of describes what happens to a neutrino and how we actually detect it. So imagine this neutrino, which is the particle coming from the bottom right of your screen, coming through the Earth, traversing all of the material of the Earth without having done anything, and with a little bit of luck, interacting near what's in the main side of the picture, near your detector. So when that interaction happens, in 1/3 of the cases, you get a particle called a muon, which is the charged particle that travels long distances. And as it travels, it makes that little bit of light, which is shown, is it blue over there? I'm colorblind, but blue, as the blue shade over there. And what you see as the round objects in there, and Keith will describe more, are optical sensors that are just trying to capture the little bit of light and the time at which it arrived. The time you need to be able to reconstruct a line out of those points of light arrival. And when you get a line, you can then point back to see what source in the sky that could have originated at. Make sense? So in the actual implementation, this is what the IceCube neutrino detector looks at the South Pole. This is to get you an idea of the dimensions, the height. Actually, let me go. It consists of 80 strings, so each line that goes vertically from the surface at the South Pole to 1.5 miles deep. They're instrumented in the last 1 kilometer, where you see the darker, heavier lines. Yes.
The strings, they're physical wires.
Yes, actually. Yeah.
Here's an example of cable.
So Keith is holding, and he'll pass, is actually a bundle of 15 cables. Each of them feeds 4 of these optical modules that are put at distance. They're 17 meters apart each, and each one can tell when a photon arrived to it with nanosecond precision. Okay, so we send that information through the same cable. So as I was saying, so the meat of this experiment is under the ice, and very pure, clean ice, very transparent, without very little radioactivity in the material. And it uses essentially all the region from the surface to the first modules that are in the ice as a shield from these cosmic rays that are all the time hitting the Earth. So you go that deep to stay away. And the little dots at the surface that you see are a cosmic air shower detector, something that actually tries to capture the cosmic ray showers that come from the top, that sometimes are correlated with events that we're interested, that go deep inside the ice. So altogether, as I said, is about 80 strings of detectors. There is going to be a total of 5,000 of these photosensors deployed when we're done. We're about 2/3 done now. Here's the sequence of the deployment. First, we deployed a few years back in 2004, 1 string, that's the dot that you see there. Then we deployed a few more. This goes slowly, and Keith will show how it's a big logistic feat to get these strings deployed 2 kilometers deep at the South Pole, very remote location. And right now, this slide is slightly outdated. Now we have 59 of these 80 strings already deployed and taking data. So how much time have we? I don't know, because I don't know. Okay, I think more or less. So this is an example of an event. This is actually a cosmic ray event. They made it. Yes. Yes. Sorry. Maybe I was making an effort to hear myself. That's good. Can you hear me? Yeah. Oh, great. Thank you. That's going to be more comfortable too. So what you see here is actually a real event in which you see first in time the top being hit. That's a cosmic ray shower that is hitting, a very big cosmic ray shower that is hitting, and each of the dots is a detector element that saw light. And then with a little bit of delay, you see how that cosmic ray shower made a whole bunch of particles, muons in this case, that are flowing down, and you can see how you can reconstruct the direction. So these are cosmic rays which are not interesting for us and not very interesting, but what are actually interesting is the few events that actually will go from the bottom up, because that means that they actually had to go through the entire Earth, and therefore by force they have to be neutrinos, and they cannot be any other particle that can traverse. The other oddity that you may observe is half the way through the ice, right there is a place where the light seems less dense, and that's because there is a dust layer. The ice is less clean down there, and that forces, essentially we get less counts. So the other main motivation for looking at neutrinos, looking at the sky for neutrinos, is essentially opening a window where you haven't seen before. And this is a table that shows that all the way to Galileo times, 400 years ago, the telescope was first used for navigation, or actually developed for navigation, but the discoveries of astronomy started there with the moons of Jupiter. And the same thing happens many times, the Hubble telescope trying to look at nebulae and then discovering essentially, or confirming, or helping to confirm the expanding universe, and all the way down, to more recently using gamma rays, where we initially were used to monitor some nuclear bomb being exploded in the Soviet Union, and they ended up observing gamma ray bursts, which are a very interesting astrophysical event. So essentially, with neutrinos, we're essentially opening a window and looking at the sky in a different way that was not available before. Yes. Actually, the gamma ray field has developed a lot. What's marked there is kind of the first time that a particular wavelength made kind of the first physics news. The field that is most active right now, besides neutrinos, which we haven't seen any source, outside of our galaxy, and we're looking. But gamma rays astronomy is the kind of the most intense field, and there's lots of discoveries being made all the time. There was a launch of a satellite just a year ago that produced a bunch of new sources of gamma rays. So it's a very, very active field of research. So at this point, probably too late, I'm handing these over to Keith for the second part of the talk.
Okay. Thanks, Azriel. I'm going to try to talk to you more about the actual construction of the detector, both some of the hardware and the software that we have. I'm going to start with the digital optical module. I'm going to turn this up a little bit. Am I good? Okay. So this is really the heart of the detector, is the the DOM, and it's basically constructed of two pieces. At the bottom is a photo multiplier tube. We have an example of one right there. If you can come up and pick it up out of the dog bowl when you want and take a look at it. At the bottom is a photo multiplier tube, and at the top is some electronics that can digitize that signal and then put a timestamp on it and send it up the cable to where our counting house is. Let's see, at the top of the DOM is some custom firmware that was built by I think almost entirely. That was the main contribution of the Berkeley Lab, the institution that we're at. I'm not a hardware person per se, but this is there's lots of interesting stuff on there. But it's I think in particular it has a pretty accurate clock on it, which is really necessary for us in order to do that time stamping, so that we can get an accurate reconstruction. Yeah.
Do you know if anything special had to be done with the hardware for the extreme temperatures that it was tested?
Yeah, quite a bit actually. Yeah, because it needs to. The environment that this lives in is pretty hostile. It's like anywhere from like 30 to 50 to 60 below zero.
It was mostly part selection, making sure that things actually, and then just testing. A lot of testing for reliability. So it's a lot of testing.
We do a lot of testing. We actually have freezers where we put these things together, or pieces of them together, and then do cycling on, freeze them down to 50 below zero and bring them back up, continually running them, looking for failures to make sure that they'll survive. That's a good question. It's pretty low. It's like 1 or 2%. 1% of DOMs well, clearly once we drop them into the ice, they're there. I think somebody calculated for like another 70,000 years, at which point they'll fall off the edge of the continent. So you can't go retrieve it or fix it. So they need to be right. And I think a 1% success rate is actually pretty good. That's 1% of DOMs that have just become completely unresponsive. There's a few special needs DOMs, if you will, that need special calibrations to compensate for particular failures or odd behaviors. But there's a ton of stories about like the gel that the photo multiplier tube sits in the bottom of this thing, and there's this clear gel, and apparently the first set of gels that we got cloudy when it got cold, and so there's 1,000 stories about this stuff. But no, the environment that these guys live in is extremely harsh, and we had to do a lot of testing to make sure that they'd survive it. Yeah? I think most of it was just making sure from the manufacturers that they would say, yes, this is going to work at 50 below zero or 40 below zero, and then we would test to make sure that it actually did. I think that's about all that I know of in terms of.
The electronics design was standard in the sense that the same thing that would work at room temperature in principle, just the parts, you need to make sure that they wouldn't flake out.
Yeah. But no, it's definitely a big concern. Here's here's a photo of a DOM being deployed. Actually, you guys can look at this. A photo of, on the left there is an actual hole that has been drilled, and that's the cable with the DOM attached to it. Now you can just barely see it at the bottom. I helped work a couple of deployments of DOMs where we actually attach these guys onto the strings and then deploy them down. And looking down a hole that is 2.5 kilometers deep and there's extremely cold air blowing up is pretty awe-inspiring. I don't think it's not quite big enough to fall down, but that certainly goes through your head as you're looking at it. And then on the right is an example of the ice top tanks. So that's kind of the surface detector. There's 2 DOMs in each of those tanks, and there's 2 tanks on top of each string. So, and that's used, like Azriel described, for either a detector in its own right or also for vetoes, for noise that comes from the surface when we're really looking for things coming up. Here you'll probably recognize I think this is a sketchpad animation of a DOM in the string of, this is working right? Yeah. So this is kind of a visualization of what the detector looks like. That's one DOM. There's all the strings. That would be the full detector. We're about halfway built with it. Here come the ice top tanks, which are just little circles in this animation. And then you can see there's our counting house, basically a data center, if you will, that sits on top of the ice. Those 2 silos are where all the cables from all the strings come up. So like the biggest racks, what do they call them? Cable trays you've ever seen in your life. So, well, I don't know, maybe you guys, being with YouTube and Google, you've seen bigger ones, but so that's a little animation for you. Here's some other photos. There's the counting house on the surface. These numbers might be a little bit out of date because 17 racks of computers, it's at 60 kilowatts. The power consumption down at the South Pole is a big concern because it all ultimately comes from burning jet fuel, because that's the only power source down at the South Pole, and that has to be flown in, which means it's very expensive. So there were a fair number of engineering decisions based on, cycles per gallon of jet fuel, or operations per gallon of jet fuel, if you will. So that's where all of our data collection, our DAC software runs down there, which I'll get into a little more details in a second. So one of the things that's interesting, certainly being a software person, is that my introduction to the project was that IceCube was a software project. For Azriel, it's a physics experiment. For me, it was a software project. And then when I actually went down to the South Pole to help install and configure some of our software, it became blatantly obvious that IceCube is a drilling project. And in and of itself, the drill is a pretty impressive feat of engineering. Basically, to drill these holes 2.5 kilometers deep down into ice, they use compressed hot water. And that the first phase of it is using what they call a fern drill. That's the picture there on the lower right. That basically melts the first, I think it's like 40 or 50 meters of what, it's not ice, it's what as skiers we might call packed powder, but it's not like a compressed drill wouldn't work. It would just spatter and wouldn't drill a hole. So this thing basically drops and melts its way down, and then after that goes the first phase. It then does the actual drill, and you can see that on the right there. This guy's driller is attaching the drill. On the upper right there is the drill house. There's a picture later of what we call the drill camp, which is where all of that water is. The ice is melted, it's heated up, it's compressed, so it's high pressure superheated water. So here's another. Obviously, we like Sketchpad, SketchUp, I think it's called. Here's another animation. So that's the fern drill going, kind of melting its way down. They pull it back up. They reattach the real drill, if you will, and then that goes down and basically blasts its way out. So there's no real navigation. Basically, we know we're going to get a straight hole because it's so heavy. It'll just drop. There are some, I think, some sensors in there to make sure that that it's not turning or curving. So there's a big spool behind it, which is a pretty impressive thing to see up close. So, okay, so let's see. We're getting into some of the software aspects of it. So there are a tremendous number of software projects around IceCube. I'm primarily involved with the data acquisition part. So, but there's, to kind of break that down, there's the in-ice embedded, that's the DOM application, that's the software that actually runs on the DOM. Then there's the ice to surface communication. We actually wrote our own Linux driver. We've got some custom hardware in the machines that these guys are actually plugged into. And then there's a data acquisition software. These all run on, standard commercial off-the-shelf hardware, Dells or HPs. I think we go back and forth as to which ones we end up using. It runs Linux. It's unfortunately at the moment it's a pretty old version, and we're trying to push to get that upgraded, but that takes a little bit of work. And then there's the data acquisition system. We've got Supernova and GRB triggers in there. After the data acquisition part, then there's this processing and filtering, and there's the transmission back up to the north over satellite links, verification, and there's also an experiment control layer that kind of sits on top of the data acquisition layer. That's how we actually drive the detector these days. Here's kind of a low level. I thought I skipped this slide, but oh well, I'll talk about it. This is a look at the low level interacting with the DOM itself. We can actually log into one of these guys and control them specifically. It's not something you do on a regular basis, but it's good for diagnostics and installation. Yeah. No, it's running its own. We basically wrote our own firmware. There's an FPGA in there and other CPU. It's actually running our own firmware. There's several different layers of it. I can't speak that authoritatively about it, but it's not. I think we originally looked at some different embedded operating systems, but for reasons that I'm not aware of, we just opted to go with our own. So. It's a good question, though. It was one of the things that we looked into early on. So, yeah, you can see we're just catting proc files and running special programs to interact with the DOM at a lower level. So the data acquisition system is the one I'm going to be more familiar with. Basically, it's a set of Java components that are basically controlled using Python software. So we basically have one component. Roughly one component per machine that are the basic interconnection and communications through standard protocols. Within those things, we're using TCP, IP. This is all communication that happens in the data center between the different components. And then on top of that is IceCube Live, which is this Java Python communication between the Python code and the Java code. And we use XML RPC for that. I'll go into more detail on that diagram in a second, but it kind of shows you that off of the ice, we have the DOMs that are down. If you look at the string hubs, those are the machines that sit on top of each. There's one string hub machined per string, and that basically collects data from each string. And then there's one hub. I don't think that's quite true. There's a couple of hubs per. There's a hub per set of ice top nodes, and that pulls up data from the ice top detector. Those guys feed their data into a series of triggers, those which look for interesting events from that data, and then that gets fed into a global trigger that looks for a trigger across the two different detectors, the ice top and the in-ice detector, and then that gets sent to the event builder, which does all the work of actually collecting the events and assembling into something that can be looked at. The Python daemons, by the way, go ahead and stop me if I'm talking too fast or you have questions. I'll do my best to fake an answer. So the Python that we have sitting on top, we've broken it up into two real separate systems. There is a command and control server that directly controls the Java components. So when I mentioned the ice top trigger and the in-ice trigger and the string hubs, those are the Java components, the event builder. And so these guys are controlled by these Python components. There's a CNC server that kind of starts them all up. There's a DAC run that starts a run, that initiates a run, tells them to start, what kind of configuration to use, how long to run for, and monitors the running of the components. I think we're doing 8-hour runs now. So it basically runs for 8 hours, stops, and then starts another run. IceCube Live is kind of the experiment control interface, the kind of public interface. There's a couple. Yeah, there's a command line interface. There's a web interface to it. And that has, I think I've got a page coming up, not the next one, but in a little bit. I'll show you more about those. But yeah.
The data that's coming from the DOM, is the DOM just running on its own
So the way that it actually works is it gets polled, P-O-L-L. So it's basically collecting data constantly, and when the string hub says the string hub would basically reaches down and pulls up the data from each DOM, and it's doing that on a continual basis. Basically, we're pulling up everything that we can get from it, and then it gets sent through the triggers, through the triggering algorithms, in order to decide whether or not that is an event that's interesting. So we have different triggering algorithms that we would run on different runs in order to decide what it is that we're looking for. So
Timestamps obviously are critical.
Right. So yeah, I haven't talked about that. That's actually a really fascinating thing to really quickly go through it. Each of them have their own clock, and as you know, clocks drift. And over the course of just a run and data collection, in between the communication of requesting data and pulling data, all the communication stops. We send out a time calibration signal that basically is we basically know the length of the string, we know the speed of light, the speed of the signal. So it gets sent down, it gets sent back up, and through some algorithms that I admit I don't fully comprehend, a time calibration offset for each DOM is then calculated and stored, so that later, perhaps months or years later, when you need to reconstruct when you need to reconstruct what actually happened, you can then say, this DOM saw this at this DOM's time, its offset is this. So you can then basically reconstruct kind of a global detector time that is going to be, I think they make claims of up to within like 5 or even 4 nanoseconds, which is a pretty impressive tolerance, which is what is needed in order to be able to accurately reconstruct, what happened where. So there's a fair amount in order for all that work, there's a fair amount of geometry knowledge that needs to be known about where the different DOMs are, because the ice does kind of move over time. And when you deploy a string, you need to figure out where it is. So I didn't mention this, but there's also flashers. The boards have little flashers where they will emit light. So we will run flasher runs where one DOM is flashing or a set of DOMs are flashing, and then we look to see how the other DOMs see that. And it's through that we can then figure out where everything is. And how often do we do them? Like once a month now, don't we? We do like flasher runs once a month in order to calibrate, in order to know what the geometry is of the detector, which is important for lots of different reasons.
Does the temperature matter, or is it just so stable that it's cold that it's always cold?
Once you're deep down in the ice, I think that it's pretty constant. I don't think that does the temperature change much over the season?
The main thing, so the temperature is very, very solid. The main effect is when you turn off the DOM, it lowers its temperature by about 10 degrees C. So when you turn it back on, you see a curve. Within minutes, you're back to thermal.
But we're generally keeping the DOMs on. We're they're on all the time. So yeah. Kind of already talked through what this slide has, but breaking down the string hubs. The string hubs is ice top hubs. They read from their respective strings and they pass it on to the trigger. Trigger uses a series of algorithms, stores a time intervals, which then get sent to the event builder. The event builder then reaches back into the hubs and pulls the actual data. So that kind of minimizes the amount of data that has to get moved around within that network that runs in there, and also reduces the load on the trigger machines and the event builder machines, which has in the past been a problem. Okay, this is actually, hopefully I got this right. I went through this morning and actually tried to get a sense of the different rates. So these are actual numbers from runs that happened, I think, yesterday or the day before. So the ice top hubs, they're seeing about 315 hits per second, which that's one particular ice top hub. String hubs about 700 hits per second, which when you combine them together, 40,000 for the string hubs and 2,600 for the ice top hubs. That's what the respective triggers see from their subsets. They then send requests onto the global trigger, and then So the global trigger then sends those requests onto the event builder. The global trigger itself is running trigger algorithms to decide what out of the whole detector he wants to see. He sends these requests. These are just the time intervals of things that appear interesting based on the results of the trigger algorithms. And then the event builder then reaches back. He actually reaches back both to the string hub and the isotope hubs. I just don't have that other line in here. And then he sends the actual readout requests back to the event builder. He then assembles the events, and we're seeing about 18,000 events per second. 80? Did I miss it? It's
2,000.
About 2,000. Okay, so this must have been a low one, or I only looked at one string and one hub because I didn't have enough time to put all those numbers together. But that kind of gives you an idea as to the flow of data that goes through these different components. Oh look, we jumped forward. I jumped all the way to the end. Oh great! I hit the wrong button. Bear with me as I get back to. I hit a button. You get a preview of all the good stuff that's coming up. Obviously, we have a lot of photos. See this? Oh, I blew it. Okay, wait, there I am. Now I'm going the wrong. Oh. I apologize for this. There's the event. Let's see. So processing and filtering. Yeah, after the data acquisition, we go to what we call PNF, and that basically does another layer of processing and filtering and then sends it up over the satellite links. Sends that data up over satellite links to the north, where more analysis and algorithms are run on it, and then eventually physicists publish papers, which is really the end goal. But wait, I'm not supposed to say that. Here's an actual screenshot of IceCube Live. This is our kind of experiment control. You'll probably notice that as researchers, we don't have the money to hire fancy UI interface people, so we end up with interfaces like this. But it's functional and it works, and I think you can barely make out there that we have a 98%, almost 99% uptime, which I think is pretty good. You can click through on all those different. Each line there represents a different run that's gone on. So this is kind of something we look at to make sure the detector's still running. So here is kind of a laundry list of different technologies that we're using. Linux, Red Hat, there's a little bit of Ubuntu. I don't think there's any Ubuntu down at the data center, but I think a fair amount of our development is usually done on Ubuntu. Let's see, we're using Python. There's actually some Perl code. There's a couple of people who like to program in Perl, and we try to give them a bad time, and they try to give us a bad time, but that's the way it goes. We've got Java. There's also GCC and C++. That's I think a lot of the analysis code is written in C++. The firmware obviously is written in C. MySQL, we're using MySQL, MediaWiki, Django. We're using Mantis and Subversion for bug tracking and version control. We were in the past using JBoss, which ended up working out to be just too overweight. We're actually using JBoss in the data center for kind of managing all the components, but we eventually tossed that out. We had a Postgres database down there, which kind of got tossed out at the same time we tossed out JBoss, because we realized it was just a little bit more heavyweight and a little more resources than we had to devote to it. So I'm going to try in the time remaining to just kind of burn through some of the pictures about what it's like to travel to and work at the South Pole. So hopefully this is more the eye candy part. So one of the things that's interesting about the South Pole is that it's actually a high altitude environment. Its natural elevation is about 9,000 feet, but because you're in the middle of a continent that's almost entirely covered with ice, the air, as it's been explained to me, actually slides off the continent, so it's thinner there than it would be at 9,000 feet, say here. So the altitude that you experience, the physiological altitude, is more like 10 and sometimes 11, and it can vary day to day based on the weather. So that's one of the first things. I mean, obviously, when you go there, you get off the plane, the first thing you notice is it's extremely cold, like 20 or 30 degrees below zero. Depending on what part of the country you're from, you may have actually experienced that yourself. And that can be, you can deal with that. You can put on more clothes. Altitude takes a couple of days. But one of the other things that took a lot longer to deal with is it's extremely dry there. I'm not someone who wears lotion, puts on hand lotion or has dry skin, but my knuckles were cracking and you get headaches, not just from the altitude, but by being dehydrated. You have to drink water constantly. It makes you seriously reconsider any coffee or alcohol consumption you do, because they'll dehydrate you as well. Let's see, what are some of the other interesting facts? It's like 30 below in the summertime and get to be 80 and 100 below in the wintertime. Fortunately, I'm not there in the winter. Summer population is about 200, maybe 300 people, or winter rovers, people who stay there over the wintertime, about 45, maybe 50. Yeah. Well, researchers and support staff, people who work there to, like the drillers and stuff. Yeah. So, the nearest, being at the bottom of the planet, there's only one day per year. The sun comes up once and the sun sets once. So if you're there in the wintertime, it's night almost the whole time. If you're there in the summertime, sun just circles over your head, which is, I thought pretty cool. Some people think it's kind of disorienting. I actually enjoyed it. There's almost nothing else that lives there. There's no like bugs or insects or anything. And the nearest city is 840 miles away. So you need to be prepared. But to get there, here's a little Google Earth application. You first fly to New Zealand and you're there. And for me, there in the summertime, this is a photo I took of all the clothes they gave me, about 40 pounds worth of clothes that you have to try on because you want to make sure it fits in the middle of summertime in New Zealand. But it's important to do that. So then from New Zealand, you fly even further south to McMurdo Station, which is on the coast of Antarctica. And if you're lucky, you get to fly in one of these, which is a C-17, which is a jet, which will get you there in about 4 or 5 hours, as opposed to a C-130, which takes about 8 hours. So this is a view inside one of those C-17s. That's actually one of our cable spools. It's one of the cables. If you pass it around, it comes on a whole spool. And you can see there's some pretty comfortable seating there, a fair amount of space. Personally, I would rather fly on one of these than your typical airline, unless I got a first class ticket, because you sit on the side, you get lots of leg room. But there's some really spectacular scenery. You look out the window and there's sea ice. You can spend your whole time staring out the window. I did. Then you land, you get off the plane with a bunch of other people. Everybody's on their big red jackets. Why red? I think it's mostly that if you're lost somewhere, you could be seen easily. There's actually, I don't know if you can see, but there's like a reflective patch, so that if they're flying over you and you're face down, it'll reflect light. That's my guess. Maybe that's it or not, but I think it's just to stand out, in a snowstorm or something. That's Mount Erebus. It's kind of weird to go to the bottom of the earth and see an active volcano, but there it is. And that is McMurdo Station itself, which some people think it's really nice. I think it's kind of dirty, but it certainly has its appeal. No, that's actual dirt. That's actual. There's actually exposed land there. So you can see off. There's a picture off in the distance of an icebreaker. They basically break up the ice once or twice a year in order to bring ships down to ship in supplies. It's always fun to see the icebreakers off. There's some spectacular scenery down there. I was there. I was really lucky. It was a nice day. I got to go out on a hike. Went up to that's Castle Rock. This is a picture of the trail out to Castle Rock, and just for a frame of reference, that's Mars. So to give you a sense of what it looks like there. Of course, can't talk about Antarctica without a photo of penguins. There's some penguins. I wasn't lucky enough to see any penguins. Did you see any penguins when you were there? No. So there's Ivan the Terror bus. So that's me. I'm just under 6'4". That's me standing next to this bus that drives around. That thing got stuck in the snow when we were driving it. Those like double dualies in the back actually got stuck in the two like amazing snow cat things they brought over to drag that thing out. Was pretty impressive. There's some really impressive machinery down there. I've got 1,000 more photos that I clearly don't have time to get through that I can show you if you're interested in seeing more. So then from McMurdo, you go even further south. This is the C-17s, C-130s. Those are turboprop planes. very loud, slower, smaller, more old school. They're a little more dense on the inside. There's some of my coworkers. It's pretty much what a flight on a C-130 looks like. But then there's even more spectacular scenery flying over the, the Transantarctic mountain range, which is basically a mountain range that is almost entirely covered in snow. So that's a mountaintop that's completely covered in snow. There's another one. It's just kind of crazy to think that's what would be the top of a mountain here. You can see amazing glacier drifts. There's a photo. I thought that was funny. You can actually see somebody sticking their camera out the window to take photos. If you're lucky, you can go up and talk to the guys who are flying the plane. I think believe it or not, it's a New York Air National Guard that has a contract for doing the transportation back and forth. Apparently, the New York Air National Guard got it because they fly in and out of Iceland, so they have experience with planes and cold flights. There's a plane landing at the South Pole. You get off the plane. And there's the new station. That's probably a couple of years old. They're building a new station. I think they're finished with it. They're finished with the construction of the new station down there. You can see it's kind of built on stilts. Yeah. No. Sorry, didn't mean to give that implication. There's many different science projects that happen down at the South Pole, and the ice cube is just one of them. It's one of the bigger ones, but it's just one of them. So there's a lot of science that all goes down there. It's a U.S. station, but that doesn't necessarily mean all the projects are just U.S. based. There's a lot of different international projects that happen. Ice cube itself is an international project. I mean, we have, some 50 different institutions from, I think, every continent on the planet. So it's not just ice cube. There's lots of different projects. There's another scenic shot of the station. It's actually built on stilts because there's a fair amount of snow drift that builds up. Very little snowfall, but a fair amount of snow drift, so things get buried, which is why the dome is being taken down because it's getting buried. There's Dave. He's one of the primary DAC software authors standing at the South Pole. You got to go out and get your hero shot. There's another Mark. He brings his golf club and likes to golf. So there's proof that I was actually at the South Pole, if you can believe what your GPS tells you. 90 degrees 0000. Took me a while to get that photo. I'm not sure what was going to freeze first, my hand or my GPS or my camera, but I finally got the photo. That's the South Pole marker right next to it. So, and there, of course, is my hero shot holding up the world. You're welcome. This is some of the luxurious accommodations you get to stay in. Did you stay in a Jamesway, or did you get to stay in the main station? You had to stay in a Jamesway, yeah. Some people, if you're important enough or have enough ice time, as they say, you can stay in the main station. It's a lot more comfortable. I'm not one of those people. I had to stay in a Jamesway, that's a panoramic shot. That's about 50 different photos. Bored one night, took a whole one shot together. But that's where I was staying. You can see this. I got the same backpack here. Still have this. So, less. That's just like a series of wool blankets and canvas between me and the outside. The plywood is to the next berth or whatever, the next bunk. So it's a little bit disturbing to like be sleeping. There's my head, like 6 inches from where it's 30 below zero. Fortunately, that was the second time I was there. I was further in towards the middle, where if you look at this, James, you see that thing sticking off the side? That's a furnace. It's probably a big enough furnace to burn my house down here, but it just heats that. And that's just they call them Jamesways, or what are they? A Quonset hut. It's a Quonset hut-like thing. It's like canvas with with some insulation in there, but a whole lot less than you would think. Those things must bleed heat. I can't believe they're very efficient. That's out in summer camp. They only have that open in the summertime to accommodate the 200 as opposed to 50 people that are there. And what do they call us? Beakers, science people who show up as opposed to the other people who work there. So let's see what else.
The floor is at freezing temperature, typically.
Yeah, the floor's pretty cold.
We're up there, uncomfortable we have.
So believe it or not, my laptop overheated in that room, and because I was, my disk died, so I had to rebuild I had to rebuild a whole bunch of stuff, but it actually overheated, and I solved it by sticking it on the floor, and it stayed nice and cool, but it didn't overheat then, and it was because the air is so thin. There wasn't a problem with the laptop. There's a really nice cafeteria down there, far better than the cafeteria we have at the Berkeley lab. Not as good as yours though. But it's still a good cafeteria. It's kind of our typical work environment. We just all sit around a table, hack on stuff. There's another shot inside the station. There's a why is the name of this escaping me? That's tomato plants. Yes, tomatoes. So they have their own. This is basically so they can grow fresh vegetables. They can have vegetables, lettuce, and tomatoes and stuff like that over the wintertime, which is pretty important. There's another scenic shot of our counting house. Some more. Oh, there's the drill camp. So that's where they heat up all the water and compress it. So use snowmobiles to get around most of the time. So I don't know if you guys have any other questions. These are just kind of fancy photos. Sure, go ahead.
I'm not sure the place, but how are you sure that
I guess probably an Azriel question.
Essentially, from the direction, if they come from the bottom up, they have to be neutrinos because no other charged particle. Essentially, neutrinos are the only particle that can cross the Earth, and the charged particle that comes from them is what you detect. If you were, so that essentially by looking down, you know that it's a neutrino, guaranteed. We can also.
there wouldn't be any spontaneous emission of electrons from the surrounding star?
Not at the energies that we're looking at. We didn't talk too much about the energy, but this is aimed for things that are tera electron volts. So there's nothing, radioactivity doesn't make anything like that, for instance, spontaneous.
But the detectors will have like shot noise every once in a while, and you can just pick those out because it's only having one detector.
That's right. Actually, the shot, what you call shot noise, is in the glass. The ice is very, very clean, very little radioactivity. But the glass that we're actually bringing down around each sphere, there is some potassium in it. Potassium has a decay that makes essentially light, but as you say, that it's not correlated with the light anywhere else. So we get a big count rate in each module that it's not in time with other modules. So most of it gets weeded out quickly.
Yeah, that could be something that could be thrown out algorithmically. If only one DOM sees something, throw it out.
So
Or
usually the whole thing is like one big point detector anyway?
Yes.
Okay, you're not trying to form any kind of image.
Well, yes, a straight line is our ideal image in time. So if you imagine
One DOM is a point, right?
DOM, if you think of DOM is at X, Y, Z, and T, and then you have a whole bunch of DOMs with different times, and from that you can reconstruct a line, a trajectory, if you were, of that charged particle that traveled from one place to the other. And that's
So when you detect it, that doesn't mean that it stops going.
right. No, actually, the charged particle typically just keeps going. You just see a little bit of light that came from it. So let me reiterate. This may be too complicated, but let me go. So the neutrino is neutral. So it comes in and doesn't make any light. The ones that do interact make a charged particle, and it's that charged particle that produces a little bit of light that is the one that you actually observe with your DOMs. Make sense? So by looking at the charged particle track, you infer that it was a neutrino that produced it. Because nothing else could have produced the charged particle going up from the bottom.
So normally you only be detected by one of these dots.
No, multiple. Our typical event is the track made by the charged particle, the new one, is typically kilometer long. So you think of the thing that is crossing at the speed of light, really the speed of light, from one side to the other of this detector. Thank you for the image. And it's making light as it goes through the ice.
so
That is going from the top down.
In this case, yes.
this particular one is a downgoing. That's coming from the top, but you can. It's hard to make out here, but you can see that the different flash of light, flash of lights. That's each DOM seeing something, and so based on that kind of, what they all saw, you could then reconstruct. You can barely make out, but there is a line that gets drawn in, which is presumably the trajectory.
Have you captured any neutrinos?
Yeah, we didn't go through that. There's a lot of neutrinos that we observe, many a day, which are what we call atmospheric neutrinos. They are of the not very interesting type because they're produced by cosmic rays that already have bent in the way, and when they hit the atmosphere, they make neutrinos. So we observe those all the time. The one that we have not yet observed, and we're of course looking for, because that would be the discovery, is neutrinos that came directly from the source. So the way we would see those is you look at the neutrino sky map, and you would see a bundle of neutrino events coming from a single direction. That will tell you those neutrinos are not atmospheric neutrinos, that actually come straight from the source. That we haven't discovered yet.
It would have to be a bunch of them. You have to see a succession.
You would need to see a few to be able to tell it from the background, which is these atmospheric neutrinos. So at least a few, about 3, 4, 5 from the same direction will do it.
So do you think that it's remotely possible to put together something like a big neutrino lens that you could eventually form images of these things?
The lens concept for neutrinos is almost impossible because the interaction, the way you can make a lens for light, that means that the photons are actually interacting with your lens, right? Therefore bending. Neutrinos interact so weakly that essentially you cannot really make a lens. So what we call this a telescope, but really what you're doing is hoping that one of these just goes through your large detector.
Do neutrinos interact with each other?
They can, but very, very...
A sort of dynamic neutrino lens out of other neutrinos.
That's a clever... I think the chances of that is very, very, very even smaller, but it's a clever concept.
So here's, somewhat related to what you're talking about. Here's a slide that we skipped, but this is a picture of the sun taken from a different neutrino detector. But that's a picture of the sun with in terms of camera, a 500-day exposure. So, and it's pretty poor resolution. So I think the idea of neutrino lens is, not terribly practical. So, any other? Yeah, go ahead.
Do you know the overall cost of this project?
Yes. It's like 270 million. Yeah.
Who funds it?
National Science Foundation. So, and there's they're the main funder, but there's other institutions, international institutions have fund European funding sources and stuff. So,
You say this is about halfway built?
the detector's about 59 strings, so we're a little more than halfway completed in terms of the construction. Of course, everybody thinks the software's done, but you always think your software's done. So we'll see when every time we deploy every time we get a new set of strings, we all bite our nails as we watch our software fall over because it can't handle the extra load, and then we have to figure out how to fix it and ask for faster hardware, or we're just about to release a new data compression, and maybe that'll save us, buy us some time. So. Mm-hmm.
How long are you going to use it?
What is a lifetime? 15 or 20 years?
15 years is the target.
Yeah.
Maybe longer. Really depends when the competition comes online.
Competition.
Yeah, there is a European smaller detector, and they are thinking also of scaling up. They're doing it on water though, not on ice, so it has different challenges.
This is in the Mediterranean?
Yes.
Okay. We should get work on that, and then we can go to the Mediterranean as well as the South Pole. Yeah. Okay. Any other questions? Or? Okay. Yeah, sure.